Hello, everyone. I'd like to welcome you to this ACUR ANU student presentation session. We acknowledge and celebrate the first Australians on whose traditional lands we meet and pay our respects to elders past and present. My name is Sneha and I'll be chairing today's session. I'd like to tell you we have 4 student presenters today and 2 judges. So today's judges are Dr. Maria and Marina, whom we'd like to welcome. And with that, let's start our presentations. Our first presenter today is Flynn. Please start whenever you're ready, Flynn.
Hey guys, so thanks for coming today. I'm an honours student at the University of Queensland and I do research in computational atomic physics. Now my work mostly focuses on testing and improving the accuracy of computational models. So today I'm going to discuss one particular correction to electron energies in heavy atoms called the Bohr-Weisskopf correction and how we improved the model for calculating this correction. Now, if you're not a physicist, that probably didn't make much sense to you, and that's okay because we'll walk through it slowly. So first, let's have a look at some key physical principles that we'll need to understand what the Bohr-Weisskopf correction is and why it's significant. So one of the fundamental principles of mechanics is that particles can be described by something called its wave function. And this is a probability density that tells us how likely it is to find the particle at any point in space. Now, it can also be used to evaluate the energy of a particle if we know it's Hamiltonian, which is just a matrix that describes the particle's kinetic energy and how it interacts with its environment. So the wave function of electrons in an atom have to satisfy this thing called a periodicity condition, which I won't get into, but just know that this restricts the possible energies that the electron can have to be a discrete energy spectrum, as opposed to a continuous energy spectrum. And if we consider different types of interactions that an atomic electron may have, so for example, interactions with other electrons in the atom, or perhaps with the nucleus, then the discrete energy spectrum changes. Now, one example of an interaction that an electron may have, which we'll look at the importance of shortly, is with the nuclear magnetic moment, which arises due to nuclear spin. So electrons, protons, neutrons, all of our building blocks for atoms have this property called spin. And if you've heard of spin before, you'll be very familiar with how difficult it is to conceptualize because it's not something we experience on the macroscopic scale that we exist on. Now, essentially, spin is a type of angular momentum that particles can have. Now, a lot of people here are probably sitting on chairs that may swivel around. If you push yourself off your desk and make your chair rotate, you'd have some angular momentum that causes you to keep on rotating. Except with spin, there's a little bit of a twist. The particles aren't actually spinning, but still do have some angular momentum. Now, if you're confused, that's good, because so am I. And you can thank the pioneers of quantum mechanics for this misleading naming convention. But the important thing to know is that because of this wacky property called spin, particles like electrons, protons, and neutrons actually act like little magnets. Oops, gone one too far. So the entire nucleus itself acts as a little magnet, which the electron can interact with, and this actually changes the allowed energies by a very small amount. And that brings us back to the Bohr-Weisskopf effect. So I mentioned it a couple times now, and what exactly is it? Well, in an actual atom, the particles inside the nucleus take up some very small volume. And although it's extremely small, even on the scale of the atom, there is a measurable difference in the electron energies if we were to use a point-like nucleus, like an infinitesimally small point, versus a finitely sized nucleus that takes up some small volume in our model. And so the Bohr-Weisskopf effect is actually a little bit more complicated than this, in that it describes the correction to the electron energies due to a finite-sized nuclear magnetization distribution, as opposed to a physical volume. So this is the simplest model of the Bohr-Weisskopf correction that there is. And all of the interesting stuff actually lies in these Ks and Kl terms. And these angle brackets here just mean that we're taking the average over all of space. So the first term here, Ks, tells us how much of the electronic wave function is in the nuclear region. So the denominator here is just like a sum over the electronic wave function across all of space. And the numerator is a sum over the electronic wave function over just the nuclear region. Now, the whole Ks term actually tells us of the contribution to the correction due to the nuclear spin, and hence the subscript S. And so the second term is fairly similar to this, except it describes the contribution due to the orbital angular momentum of the nucleus. So just like regular angular momentum that we're familiar with. Now you can see here that in the expectation values of the Ks and Kl terms, that the Bohr-Weisskopf effect actually depends on the nuclear wave function, this U of R term here. And this makes sense because the nuclear wave function just gives us information about its magnetization distribution, which is exactly what the Bohr-Weisskopf corrects for. So a more complicated model for the Bohr-Weisskopf correction, which is currently being used in the literature, also takes into consideration two additional contributions. First of all, spin orbit interaction and antisymmetry. Now, it's not super important to understand what these two terms mean, but essentially the spin orbit interaction describes a coupling between an electron's spin, which remember is just a type of intrinsic angular momentum, and its orbital angular momentum, which you can think of just as regular angular momentum of a rotating object. Now, the antisymmetry term is a little bit more complicated. It just comes from something called the Pauli exclusion principle, but I won't talk about that today. So now that we've discussed what the Bohr-Weisskopf correction looks like, let's have a look at how we actually calculate it. So current methods for evaluating the correction generally use a very simple step function to describe the nuclear wave function. And the reason for this is because it's very easy to evaluate these integrals, the Ks and Kl terms, using a step function, since the wave function just goes to 0 after some point. So you don't actually have to calculate the integrals all the way out to infinity, and it's a lot computationally easier. However, this is real life, so obviously things aren't quite as simple as this. The wave function of the nucleus is generally quite complicated, and because of this, it can be rather difficult to evaluate these Ks and Kl integrals numerically to obtain the Bohr-Weisskopf correction. However, using a more realistic nuclear wave function will give us a more accurate estimate of the Bohr-Weisskopf correction. So to get around this issue, we first determined the general expression analytically for the Bohr-Weisskopf correction, just using an arbitrary nuclear wave function. And so then we can construct an accurate nuclear wave function a bit later. Now, as I mentioned in the beginning, the Bohr-Weisskopf correction is the correction due to a finite nuclear magnetization distribution. So of course, it must depend on, well, exactly what the nuclear magnetization distribution is. Now, so finding an expression for this f of r term here, the nuclear magnetization, is sufficient for estimating the Bohr-Weisskopf correction. And now that we have a model for computing the Bohr-Weisskopf correction using an arbitrary nuclear wave function, we can begin to construct some complicated looking wave functions and check if our correction matches the literature. And this is actually the next step, which is still being worked on currently, to evaluate the nuclear wave function using a more sophisticated method than just a step function. We aim to construct accurate nuclear potentials and determine the wave function numerically by just solving something called the Dirac equation, which describes the dynamics of fermions, which are the type of particles that make up atoms. Thanks for listening to me, guys.
Great, thanks, Flynn, for that great presentation. So we have around 5 minutes of Q&A now. Judges, do you have any questions?
Yes, I have a brief question, please. Flynn, thank you so much for your excellent presentation. Thank you as well for the great effort you made to make this understandable for people who don't have a background in physics. It's greatly appreciated. I have one question, and that would be how your improved algorithm could be actually used in future. What kind of significance or implications that has for like real life?
So precision atomic physics has quite a lot of implications, mostly in applications, mostly in precision tests of the standard model. So basically, once at this stage, most of our computational atomic models lack the same precision as experimental data does. So at the moment, experimental data is significantly more precise than our computational models. And if we improve the precision of our computational models, what we can do is actually use those to compare to our experimental data, and from that identify the possibility of new physics that we haven't yet discovered in our theories and our models. In particular, things like atomic parity violation in heavy atoms like cesium and thallium are of interest to a lot of people in atomic physics. And so you may have heard of like atomic clocks, for example, that uses cesium atoms. And knowing something, this atomic property called the G factor of the nucleus will actually give us a lot of information as to, will allow us to construct more precise clocks, basically.
Thank you.
Actually, I am supposed to give the same question, but I guess you have already answered it. Thank you so much for your great presentation.
Are there any
Thank
other
you, judges.
questions?
Yeah, so Flynn, we have another question from the audience. So is there any limitation in terms of computation? Like, do you need to use supercomputers for calculation? And the other part of the question is your experiment more like a simulation?
Yeah, so all of the work that I'm doing is computational based. So I'll write some code, run that, and then I'll calculate a bunch of atomic properties and stuff and solve some equations. For this work in particular, it's absolutely capable of doing it on just my laptop, a regular computer. But for more advanced computational models, so some of the stuff that I'm working on now actually in my honors project is implementing some higher order corrections to evaluate very precise atomic wave functions. And that sort of thing will require like a supercomputer, just because of the computational time it takes to evaluate all of the terms over all of the possible states that the atomic wave function can have.
Great. If you have any other questions from audience, can you please put it in the Q&A, or you could raise your hands and we could go ahead with that. If not, then I'd like to thank Flynn again. Thank you for a great presentation. Let's move on to our next presenter. Yep. So our next presenter is Martha. Please start when you're ready.
Can everyone see my screen just before I start? Awesome. All right. Thank you and hello, everyone. Today, I'll be talking about some work that I did over the course of an experimental summer project and a theoretical semester 1 extension project this year in the ANU Department of Nuclear Physics. So nuclear physics is a really useful and interesting field because nuclei are all around us. Everything we see and feel around us is made almost entirely of nuclei. So understanding how to manipulate them has diverse applications across a range of fields. This includes stuff like medicine, energy, and industry. So to start off simply, what is a nucleus? The nucleus is the core of an atom, which is something you might already know, and it's made up of protons and neutrons, or what we like to call nucleons. So looking at pictures like this one, it's kind of easy to assume that the nucleus is just like a conglomeration of protons and neutrons sitting in like a static blob in the middle of an atom. But in reality, nuclei are highly complex quantum systems which are constantly evolving according to a detailed set of quantum mechanical rules. And it's these rules that nuclear physicists are trying to work out. So one model that we have for how nucleons arrange themselves is called the nuclear shell model. And it describes the way that protons and neutrons arrange themselves in shells, kind of similarly to how electrons arrange themselves in shells outside in the atom. And so when you have a closed shell, it's similar to like having a noble gas where there's a closed shell of electrons and it exhibits extra stability properties. But the difference is that in nuclei, you have closed shells of protons and closed shells of neutrons independently. So you can actually get special cases where both of those shells are closed and you get even more stability in your nucleus. So this is what we call a chart of the nuclides, and this is a small region of it, and it's just a chart of every kind of element and nucleus that we can make. And so along the upwards direction, we have the number of protons, so that determines what element it is. And then across the horizontal direction, we have the number of neutrons, and that determines which isotope it is. So you can see this column here in black that's a shell closure at 126 neutrons. And across here in this black row, we have 82 protons, and that's a proton shell closure. And you see just in the junction of those two, we have this nucleus, lead-208. And so that's what we call a doubly magic nucleus because it has two closed shells. So we can describe a lot of the properties of nuclei based on where they fall with respect to these shells, and that's what the shell model kind of does for us. So close by, when you're looking at a nucleus like lead-209 here, this has one neutron outside a shell closure. So it has what we call single particle behavior, where all of the different behavior of the nucleus is just defined by the movement of that single particle. But if we go a long way away from the shell closures, the behavior is actually due to the movement of a lot more nucleons because there's a lot more outside of the shell closures. And so they start moving around all together, and that can look like the whole nucleus rotating or vibrating, and that's what we call collective motion. So the shell model describes those two extremes quite well, but what we don't understand so well is what happens in between. So in this investigation, we were looking at these three polonium isotopes that I've outlined in red, and these are in the region nearby lead-208, but a bit further away from the shell closure. And what we're trying to do is to quantify the transition from the single particle behavior near lead-208, the transition from there into the collective behavior further away by sequentially removing two neutrons and seeing how that changes the nucleus's behavior. So we can actually draw pictures called level schemes that tell us a bit about what's happening in the nucleus, because nuclei have different excited energy levels. And so each of these horizontal lines in these level schemes represents one of these excited states. So that might be a single particle excited state where one nucleon has extra energy, or it could be a collective state where all the nucleons are doing something with more energy. And so we can represent them as horizontal lines, and these vertical arrows between represent transitions between states. In these cases, so these are the level schemes of the three isotopes we looked at. These decays are gamma rays, which are emitted as the nucleus relaxes from a higher state to a lower state, and they're released at very precise energies that correspond to the difference in energy between the starting state and the finishing state. So how do we actually measure these? To start with, it's not quite so simple because we can't go out and find polonium in these isotopes in the world because it's not naturally occurring. So we have to make it. And in this investigation, we used the ANU's Heavy Ion Accelerator Facility, which is a big particle accelerator that you can see on the left here. And we basically got different isotopes and smashed them together really, really fast to produce the polonium isotopes we wanted. And then using gamma ray detectors, we recorded information about the gamma rays coming off those, like energy and the time of arrival of those gamma rays. And in this case, we actually had to use a special kind of gamma ray detector called a lanthanum bromide detector, which is different to what we'd usually use, which is like a germanium detector, because the lifetimes we're measuring are really, really short. They're on the order of 10 picoseconds. And so the germanium detectors we usually use aren't actually able to measure lifetimes quite that short. So we have all this information about the gamma rays. How do we actually get lifetimes out of that? So if we have a level scheme like this one on the left, we might have a state up here, which decays by releasing this gamma ray into this red state in the middle, and that decays again, releasing another gamma ray to the level down the bottom. So if we measure the time that we see that first gamma ray, which we'll call the start time, and then we measure the time that we see the second gamma ray, which we'll call the stop time, then the difference between those times can tell us about how long the nucleus was in that state in the middle. So actually it's a bit more complicated because there's a lot of intricacies about calibrating the detector setup to make sure there's no delays. So rather than actually doing an absolute calibration, what we do is we subtract the start time from the stop time for half of the data set, and we subtract the stop time from the start time for the other half. So we do the same thing in reverse. And what this gives us is the two data sets that you see in this graph over here. So one of them is the start time minus the stop time. So it's the data set is shifted by the lifetime in one direction, and the other one, the data set is shifted by the same lifetime but in the other direction. So theoretically, these should be shifted both around 0, but in reality, it's not quite like that. But we still have that the difference between the centers of each of these peaks should be 2 times that mean lifetime, regardless of how far it's shifted. So that's how we extract the lifetimes from that data. And this is what we've found in this investigation, is we've got 6 lifetimes in this column. So they're all quite short, which is why they're so hard to measure. And so these 3 here, you can see we have literature values from another paper from 2019. And our values agree very well with those, which is great. And very excitingly, we have 3 other measurements in red here, which are completely new. So there was no literature values for those. So those will give us some brand new information about that developing collectivity. So this is all very well and good, having these lifetimes, but it doesn't actually directly tell us anything about the collectivity we're interested in. So what we have to calculate is a value called a transition rate. So the transition rate gives us an indication of the number of nucleons moving, and it's calculated straight from these experimental lifetimes. And so a value of around 1 indicates that there's about 1 nucleon moving, so like in the single particle dynamics. A value a lot larger than 1 indicates that there's a lot more nucleons moving around, so the nucleus could be vibrating or rotating or something like that. So here are the results from my lifetimes. I've extended this graph to include a few that I didn't measure, just up to that shell closure at a mass of 210. And so you can see that there's kind of a constant value of the transition rate from 210 down to about 206. And then we get this turn off and it starts increasing. So what we're seeing there is that development of collectivity that we anticipated further from that shell closure. So that's really interesting, and it's great that we can see that sharp turn off because it tells us that it's somewhere around 4 neutrons below that shell closure this starts happening. But even more interestingly, I've got some calculated values, which are values that are predicted from the shell model. And so you can see that they agree around the 210, which is great. We don't have an experimental value for 208, but once we get back down to 206, they actually disagree. And so that means that the collectivity we see is not only increasing further away from the shell closures, but it's increasing more than was predicted by the shell model, which is very interesting and something that we'll look into further with more calculations. So in summary, we ran a successful experiment to measure 6 lifetimes, and 3 of those were completely new measurements. Our data shows that the collectivity is beginning to develop once about 4 neutrons are removed below that shell closure. And additionally, comparisons to calculations suggest that this collectivity is beyond that predicted by the shell model. Thank you, everyone.
Thank you, Martha, for that great presentation. Judges, do you have any questions?
Hi, good day to you. I
Hi.
would like to give this one question. What do you think would be the most significant impact of this study in the field of physics?
Sure. So I think initially, with more research into this, this might lead to the updating of some of our theoretical models. So the shell model is quite like fundamental, and initially this could lead to something like you know, an update of some of the ways that we implement that. If it turns out that it's bigger than that, it could lead to, I mean, theoretically, an overhaul of the shell model to something more updated and new, which would be very interesting. And all of this kind of is, all of the models that we've got here are used to predict the behavior of nuclei. And so the better we can predict them, the better we can use them to do things like, you know, nuclear medicine and nuclear power and things like that.
Thank you.
There's no question for me. Thank you very much, Martha.
Thanks.
I have a question actually.
Sure, go ahead.
Yep. So with the shell model, I was wondering, is this the physical distribution of the nucleus that you're looking at? And also, have you tried looking at other nuclear models besides the shell model? So like the Bohr model, for example, I know is another one widely used in the literature for like your theoretical estimates.
Yeah, so the shell model isn't so much a physical distribution. It's actually, it was discovered empirically because there were observations going on that kind of noticed that at these values, so these ones like the 126 and 82 and stuff, they're very high up, but they're a lot lower down. You see like a lot more naturally occurring isotopes that are falling into these magic shell closures. And so it isn't so much a physical distribution, but it's more of a how the nuclei behave. So as I was saying, like the single particle behavior outside, when you have shell closures, all of the excited energy states are due to the behavior of the particles outside the shells rather than inside the shells. So yeah, in terms of using other models, this is kind of not, because it's not a model of distribution, it's just like it's a fundamental like framework that kind of sits over which nuclei we can produce. It's not one that we have like another kind of model that describes the same thing that's quite so prominent.
Okay, thank you.
Great, Nico, you could go ahead with your question.
Thank you. Great talk, Martha. I was just curious about that final graph you showed where you kind of show your measured distribution compared with what the literature has it, or even where you calculate it should be. Why does it appear that the error bars on your distribution seem to increase as you move towards the left-hand side? Is there any physical interpretation of that?
Well, so the physical reason behind that is the lifetimes are getting shorter, and because of the way the uncertainties are arranged. If you take a look at this, so the only ones I've actually used are the 4+ states here. I haven't used the 2+ states because I only have an upper bound on those lifetimes. But the uncertainty is about 7 picoseconds for all 3 of my measurements, but the lifetime itself gets smaller. And so based on like what the relationship between the transition rate and the lifetime is, that the result of that is that the error bars look larger, even though the uncertainty in the lifetime is smaller, just because of the relationship between the lifetime and the error.
I see. Okay. Thanks for that.
Great. Hey, Martha, we have a question for you from the audience also. So you mentioned that there's a shift that is delta C in reality. What factors can contribute to this?
So I assume you're talking about this one here. So actually, this is quite complicated because there's various things going on, but we have this factor. So this is the actual equation for it. So delta C is 2 times the lifetime plus this factor that we call the prompt response difference. And that is a characteristic response delay from the setup, which is energy dependent. And so I also have the prompt response curve here that we use for the experiment, which we calibrated based on known sources. So this is like the energy dependent delay of the detector setup. And so that goes into that as well. But the advantage of this is that once you have this delta C, you only need to worry about that correction in addition to the 2 times the lifetime, rather than an absolute delay of the detector setup. So you don't have to, because obviously the 2 gamma rays are measured by 2 different detectors. You don't have to worry about how long it takes the signal to get from the gamma ray to the data acquisition or anything like that. You just have to worry about the relative time between the 2, if that makes sense.
Great. Thanks for that great presentation, Martha. Now let's move on to our next presenter for today. So our next presenter is Nico. Please start whenever you're ready.
Thank you very much. Awesome. Let me. There we go. Can I confirm that everyone sees my title screen?
Yep.
Perfect. Okay, great. Hello, everyone. My name's Neco. I'm one of the Bok Honor Scholars here at the Research School of Astrophysics and Astronomy at ANU. And today I'm going to talk a little bit about some of the work that I've been doing during my thesis, which has been focused on trying to understand how magnetic fields evolve within the environments that they exist. So let's start by just talking about the dynamics of galaxies. Galaxies are these incredibly large-scale phenomena, very large-scale systems with lots of different physics taking place, dictating the dynamics within the galaxies. And all these physics take place over very different spatial and temporal scales. But today I want to talk about magnetic fields. Now, based on our theories of the universe, we know that magnetic fields play an incredibly important role, and we observe it to be a very ubiquitous phenomena. We observe it everywhere. One of these environments that we observe magnetic fields playing an incredibly important role is star formation. Now, we know star formation, based on our observations, is a very inefficient process. What I mean by this is that the rate at which the gas and dust within these star-forming environments actually accrete into forming stars is very, very inefficient. A very small percentage of the gas actually gets converted into stars. Also, the star formation rate is incredibly low. The number of stars produced within, for example, the Milky Way is roughly between a handful and 2 handfuls. A very small number of stars are actually produced. This whole process is very inefficient. And when we run simulations and we start including different physics within these simulations, for example, this one I'm showing at the top right, we observe that magnetic fields play an integral role, not just in explaining the distribution of gas within these environments, but also the star formation rate and the star formation efficiency. So magnetic fields in our theories play an incredibly important role. Now, I just want to convince you real quick that magnetic fields are very much a real phenomena. They're not just a thing that we've postulated to explain our problems away. We do observe magnetic fields. And here I show you the Messier 82 galaxy. It's a starburst galaxy. Here we have a side-on view from Earth, and it's a composite image. Over here we have gas being ejected from the galaxy. And this study by Lopez Rodriguez earlier this year was looking at the orientation and configuration of magnetic fields within this galaxy. And it's clear that magnetic fields are incredibly large scale. They're also incredibly important. They're guiding the outflow from this galaxy. But when we compare magnetic fields in the early universe with the present day universe, it's clear that they're very, very different. Something has changed. In the early universe, magnetic fields are very small scale and they're very, very weak. In the present day, they're very large scale and very significant. And the question naturally becomes, how did magnetic fields evolve from being small scale to large scale, weak to strong? And this is where dynamo theory comes in. Now, dynamo theory is one of the most plausible theories that describe how magnetic fields are able to evolve. And it does so in actually a very simple environment. The strength of dynamo theories is that one can ignore most of the physics that we addressed at the start: gravity, chemistry, temperature gradients. All those things can be ignored. All you need to explain how magnetic fields evolve is a turbulent environment with magnetic fields. And these magnetic fields need to be weak initially. And what this theory predicts and describes is these field lines, because they're so weak, are just being passively advected by the turbulence. And as this takes place, the magnetic field lines stretch, they twist, they fold. And every time this process takes place, the magnetic field grows in strength. And in this theory, people have started making some very precise predictions about on what scales we predict magnetic fields should be concentrated. Should they be concentrated on scales comparable to the turbulence, on scales smaller, on scales bigger? On what scale should magnetic fields be concentrated? And these theories are analytic, I should point that out. So we wanted to know, do these theories only exist within the page that they've been written? And now we can test these things. We have the compute power to actually simulate these phenomena and study how magnetic fields depend upon their environments. And to do so, we have to kind of probe the plasma and see how the field evolves. One of these parameters that we probe is this Reynolds number. It's a parameter that describes how unstable a fluid is. In 1883, Osborne Reynolds who this parameter is named after, showed that by injecting ink into a pipe and controlling particular parameters in the setup, you're able to change the Reynolds number. And I won't go into detail here, but the Reynolds number is just defined as follows. You have the velocity, you have a typical length scale in the problem, and then you have the inherent viscosity of the fluid that you're dealing with. But if we just have a look at the Reynolds number real quick, Osborne showed that when the Reynolds number is sufficiently low, one achieves laminar flow. What I mean by that is the flow is incredibly coherent. It's very well defined how the flow will evolve. If you increase the Reynolds number a little bit, you start observing these instabilities forming. And if you increase the Reynolds number even further, one achieves a turbulent flow when the Reynolds number is sufficiently high. And turbulence is often mistaken for chaos, randomness. I mean, there are a lot of parallels, but there are some nuances in the definitions of turbulence as opposed to randomness. Won't discuss those, but the important thing to point out here is to study turbulence. It's very difficult. It's very difficult to predict exactly where a parcel of fluid will be sometime step forward because the flow is so complex. So what we do instead is we approach this from a statistical perspective. We decompose the flow into its different modes, into the different sized vortices. And we look at the energy spectrum. And that's exactly what this energy spectrum describes. The energy spectrum describes, on average, at a particular scale, how much energy are within these vortices. And this is a very useful way to think about turbulence because one can define these very key scales. It's a very multi-scale phenomena, but one can define these key scales, for example, the driving scale where energy is injected into the system, the dissipation scale where energy is removed from the system, and how energy is transferred between scales. And this is a much more useful way to describe turbulence. We'll come back to this in a second. Now, to actually study how magnetic fields depend upon the turbulent environment, we ran a large number of simulations and we had to run this on a supercomputer. It's very computationally expensive to run these simulations, roughly taking up 60 terabytes worth of storage and 6 million compute hours. I mean, it was a real computational task. Now here I show you two of my simulations. On the top, it's a simulation where we've set the Reynolds number to be 500. On the bottom panel, we triple the Reynolds number to 1500. And visually speaking, when we take a look at a slice of our simulation domain, by increasing the Reynolds number, we start finding energy becomes concentrated at smaller scales. On the left, we're looking at the kinetic energy. This is tracing the turbulent field. And on the right, we're looking at the magnetic energy. And we observe when the Reynolds number becomes larger, energy becomes concentrated at smaller scales. We also observe magnetic fields grow in strength. And we see this when we have a look at the magnetic energy as it evolves with time. Here we plot the magnetic energy relative to the kinetic energy. Remember the kinetic energy, the turbulence is driving the magnetic field. It's injecting energy into the magnetic field. And initially we set our magnetic field to be weak, much weaker than the kinetic field. Here you see unity. And almost immediately we observe the magnetic field starts growing exponentially. And in this phase, we have that process we were discussing before, magnetic fields amplified by the stretch twist fault model. And this process keeps taking place until there's enough energy in the magnetic field to actually start resisting the stretch twist and fold process from taking place. Now there's enough energy to resist the stretching, twisting, and folding. And this is when we go into this saturated phase. Now to study exactly how the magnetic spectrum depends upon the kinetic energy, one can characterize the plasma by looking at some key scales. Here, based on some models that we derived, we extract some 3 scales. We can characterize the kind of plasma we're dealing with by measuring these 3 scales. We have the scale where the magnetic energy is concentrated, the peak scale. We have the scale where energy is removed from the magnetic field, and we also measure that for the turbulence, the kinetic field. And then we study the dependencies between these scales and exactly how the magnetic energy spectrum depends upon the kinetic spectrum. And one of the key results of my work is that we show that there's this dichotomy taking place. When the velocity field is not turbulent, when the Reynolds number of the flow is incredibly low, we observe that the flow, the plasma behaves very differently from the flow when it is sufficiently turbulent. When it's stochastic in nature, we find that the flow behaves very different from when it is sufficiently turbulent. When it's sufficiently turbulent, we find that the peak scale depends upon the dissipation scale. That means that when we set the magnetic properties, the magnetic dissipation scale will define where the magnetic spectrum will peak, where magnetic fields will become concentrated, which is in stark contrast to some theories. Now, I'll put my summary slide up, and I just want to thank you all for listening. If you have any questions or anything you'd like me to clarify, please feel free to ask. Thank you.
Thank you for that great presentation, Neco. Judges, do you have any questions?
Sorry, let's go back.
Yes, I have a brief question, please. Thank you very much for your presentation, Neco. I was wondering whether during your investigation you faced any surprises, whether there was anything that you found that surprised that you didn't expect or didn't see coming?
Yes, is the short answer, and I'll quickly think about a quick example. I mean, for a long time, these theories have sort of just existed on the page. It's been very computationally expensive to run these simulations, and that explains why very few simulations like these have actually been run. Now we have the compute power and we can test these things. And it was surprising to start finding limitations within the theory. For example, finding that the turbulent field actually needs to be sufficiently, the flow needs to be sufficiently turbulent. There are some other interesting relations that we also find that's really quite interesting. For example, if one looks at the spectrum, the way one can actually define analytically where this scale should be, it depends upon some other properties of the spectrum as well. For example, there's this slope up here that I don't want to go too much into the theory, but essentially this is there's a power law that sort of increases from these very large scale to smaller scales, and this is actually where energy is being transferred to the dissipation scale, and you can measure the power, the slope of the power law, and you find that this peak scale actually depends upon that, and that's another one of the key results here that I don't think people have actually analytically predicted, but you can kind of pull that result out just by simulating these things and measuring these scales. That was a pretty surprising result.
Thank you.
I see there are some other questions from the presenters. Martha, did you have a question?
Yeah, sorry, I'm not certain if this is actually, a relevant question or not. I was just wondering, I forget what it was called, the thing where the magnetic field like twists and like merges on top of itself. Do your results give any like, do your results say anything about this, or are they just assuming that this is true? Like, do they give any kind of evidence that this is what's happening, or does like the scales of turbulence or anything tell you that like this is the scale things are twisting and like merging on? Like, what's the relationship?
That's a great question.
There?
That's a great question, actually. And this mechanism is actually not something that we've been able to measure directly in our simulations yet. This is a mechanism that sort of sets the foundation for the analytical work that people have done. And I mean, our theories, that our results align with what the theories measure that are sort of based upon this mechanism. But no, it's actually very difficult to track these magnetic field lines as they evolve. I mean, yeah, it's a very computational, difficult task. But we're actually working on a project where we are trying to figure out, because it's not straightforward. It's not very trivial to actually just look at these field lines. It's not like one can kind of just do these integrals in the field and kind of track how they evolve. It's a very difficult process. But no, there's no actual way yet to kind of measure whether this is the mechanism that's actually taking place. There are some debate within the theory, but it does seem like this is the most plausible mechanism as to how the magnetic field can actually amplify. I hope that's clarified that.
Yeah, thanks, and great presentation. Thanks for that.
Thanks, Martha.
So we have a question from Flynn. Before that, Dr. Maria, do you have any question? Or Marina, do you have any questions?
I guess I don't have any questions at all. That was greatly presented. So the others can proceed with their questions now.
Thank you.
Great.
Yeah, I was wondering what actually causes this distortion and aberration in the magnetic fields in galaxies?
Are you referring to this image over here?
Yeah.
Okay. Yeah. So, are you asking why does it kind of look like?
Yeah. So I'm
you
wondering
see these field
what
lines
sort
that
of
are
things influence the aberration in the magnetic fields there.
Sure. Okay. So you can see that these are actually quite small scale structures if one compares this relative to the galaxy. Maybe first I should just clarify how these things are actually measured. So one can probe magnetic fields within very distant systems. This is actually not my thesis, but just some background. One can probe the orientation of magnetic fields in distant astrophysical objects by kind of looking, measuring their polarization, how much, so there's dust within these galaxies, and then magnetic fields kind of orientate these dust grains. I'm just trying to jog my memory here. And we can kind of measure that orientation. What's affecting that? Well, there's turbulence. Turbulence is a big player in galaxies. Of course, magnetic fields are actually setting the orientation of these things, but magnetic fields are being affected by other phenomena like outflows, like you see over here. Turbulence. Turbulence actually is one of the key contributors to kind of creating very small scale structures. Yeah. Yeah, I hope that answers the question.
Yeah, thank you.
Awesome, great. Thanks for that presentation, Neco. Now let's move on to our next and final presenter, Rosemary.
Thank you.
Okay, can you all see this?
Yep, you can see the screen.
Okay, fantastic. Hello everyone, my name is Rosie. Today I'm going to talk to you about a research project that I did with the Corey group at ANU. Now this group looks at computational biophysics, and I looked at something in particular we call thermophoresis. Now, from talking to lots of people about thermophoresis, I've discovered that not very many people know what this is, and this dismays me greatly. So hopefully today I can rectify that. Now, thermophoresis is the tendency for particles to move under a temperature gradient. It's this self-heard of phenomena, but more intriguingly, we don't actually know why it occurs. Now, this forms the primary question that my research attempted to answer, namely, why do particles move under a temperature gradient? Thermophoresis, we sometimes call it thermodiffusion or the Serre effect, is the tendency for bulk directional particle motion under the influence of a temperature gradient. Now we see it on a wide variety of scales, so in ionic solutions, in colloidal suspensions, in gaseous mixtures, essentially anything where we have mobile particles. Now, put more simply, the application of a temperature gradient induces a concentration gradient. So there we are. Okay. And a very natural question to ask is sort of what direction is this concentration gradient? Now, you know, like most good questions in science, the answer is it depends. What does it depend on? Lots and lots of things. So things like particle mass, particle size, the average temperature of the system, the average concentration of the system, many, many, many factors. And these all contribute to why it's such a complicated phenomenon. Now, let me just give a little bit more context to this problem. It's by no means a recent phenomenon. It was first observed in the 19th century, yet we totally lack microscopic theoretical basis for why this occurs. And consequently, predictions about thermophoretic phenomena are really limited, and this limits the scope of application, particularly quantitative applications. Now, I'll give a little bit of background theory that we do know. So thermophoresis is governed by a diffusion equation here. Now, don't worry about the maths too much. Essentially, it's just composed of two terms, a standard diffusion term and a thermal diffusion term that comes from the presence of a temperature gradient. Now, D is the diffusion coefficient and dt is the thermal diffusion coefficient. And J here is the particle flux. So when this is 0, this corresponds to our system being in equilibrium, so we don't have our temperature gradients changing. And we can actually solve this equation to get something called the Serre coefficient, which is this ratio here. Now, it's important because it defines the magnitude and direction of the particle behavior. So in particular, if we have a Serre coefficient less than 0, this corresponds to thermophilic behavior, so the particles like to be in the hot side, and if it's greater than 0, it corresponds to thermophobic behavior, so the particles like to be outside. So I'm going to restrict my discussion to ACUR systems now. So this is systems of water as a solvent, and these are primarily what I looked at. Now it's just like this. It's been hypothesized that thermodiffusion is driven by changes in solvation and ionic shielding entropy. Furthermore, it's also been posited that, if we assume a local thermodynamic equilibrium, this Serre coefficient is really given by the negative of the change in solvation entropy divided by kBT. And this is quite important because it has significant predictive power, namely that, the sign of the change in the solvation entropy alone is what dictates the sign of the Serre coefficient, and therefore what direction these particles actually move. So this is the hypothesis I'm actually testing in my research, namely what this equation holds true. And interestingly, this coefficient can actually change sign with temperature. It's been witnessed in bulk solutions that if we change the average temperature, so that's particularly fascinating. Now, literature really currently focuses on bulk solution thermophoresis, but a very natural question to ask is, can this occur for single particles? And this is a very important question to ask, because as physicists, we like to sort of look at microscopic phenomena and extrapolate those laws to explain macroscopic effects, things like thermophoresis. And this is research. So I'm really asking, can we see thermophoretic behavior for single ions? Now, onto my actual research. I've broken into 2 key objectives. So the first is to isolate the solvation entropy mechanisms for single ion thermophoresis using molecular dynamics methods. Now, if you don't know what molecular dynamics are, they're essentially where we simulate our molecular system computationally by looking at all the intermolecular forces and then from there extrapolating the dynamics. And the reason why we use molecular dynamics here is because it's been shown to replicate thermophoresis before, but also we're looking at the scale of single ions. So this is very difficult to do at a lab scale and much easier to actually computationally simulate. Now, the second objective is to investigate potential Serre coefficient sign inversions for single ion thermophoresis. So I said before, the Serre coefficient can change sign. Now, an interesting question is whether single ions can also change their behavior depending on the average temperature. So this is something I'm looking at. Now, onto my actual methods. The systems that I simulated consisted of 2 water spheres, and they were both at constant temperature. And one was at a cold temperature and one was at a hotter temperature. Now, I placed an ion in the center of the cold sphere and then moved it to the hot sphere and measured the change in free energy. And I did this for both sodium and chloride ions. And the reason why we care about the change in free energy is because this is an indicator of the spontaneity of the process. So if we have a negative change in free energy, this corresponds to a spontaneous process and vice versa. So it gives us a really useful proxy for where the ion prefers to be. We also measured the change in solvation entropy, and that was to test the hypothesis that I was referring to before. And I've just repeated this process for various temperature differences between the spheres. Okay, so now going on to the actual results. Oh, firstly, this is sort of what the simulations look like. Just visualize this a few frames. Okay, so now looking at the results, the first free energy results. Now on the y-axis, I have the change in solvation free energy as I move from the cold sphere to the hot sphere. And on the x-axis, I have the average system temperature. So this is not the temperature of one sphere, it's the average between both of them. Now, if we have a look at this data, the first thing we see is that yes, single ion thermophoresis does indeed occur for sodium and chloride. Why do we know this? This is because the free energy change is not 0. They're clearly showing a preference to be in one of the spheres. And you can see I've also split it up into thermophobic and thermophilic regions. But we also noticed something that sodium and chloride tend to be broadly thermophobic, so they prefer to be in the cold sphere. But we noticed something funny at 260 to 270 Kelvin, and we see an inversion point. Suddenly, this sodium ion actually prefers to be in the hot sphere. But we don't see this for chloride, and this is a very intriguing result and one that really warrants further research in this inversion regime. Also, for bulk solutions, we see bulk solutions of sodium chloride, and previous research shows that the inversion point does happen around there. So, yeah, it really provides further interest. Okay, now onto the main data. This is the solvation entropy data. So on the y-axis, we have the change in solvation entropy as we move from the cold sphere to the hot sphere. Now, if this were to confirm the hypothesis I presented before, what we would see is that this would look very similar to the free energy results. But what did we actually see? Here's what the data looks like. So as we can see, we can't actually confirm or deny this hypothesis, sadly. What this shows is that our systems haven't equilibrated, but we do get a methodological result. And that is that if we have convergence in our free energy data, the corresponding solvation entropy data is not necessarily convergent. So the way to mitigate this is just simply to run these simulations for much, much longer. So yes, sadly, I can't make a comment on that hypothesis, but it still leaves it an open question. Okay, now, so some of the key conclusions I want you to get from this presentation is that yes, we've witnessed single particle thermophoresis. It can occur in the absence of bulk solution effects. We also see that free energy convergence does not imply solvation entropy convergence for molecular dynamic systems. Now, looking at the second objective, we see a very weak tentative sign inversion for sodium, but entirely thermophobic behavior for chloride. And this discrepancy warrants further research. Okay, so why do particles move under a temperature gradient? Perhaps it's due to changes in solvation entropy. Perhaps it's due to the many other system effects. But I think the better answer is that, this is a really complicated phenomenon that just requires more research. So, hopefully like an ion moving in a temperature gradient, this field can see some movement towards progress. Thank you for listening.
Thank you for the great presentation, Rosemary. So judges, do we have any questions?
No question from my side. Thank you very much for this great presentation.
No worries, thank you for listening.
Hello, I would like to give my question for that presentation. So here goes my question. What do you think is are the significant changes that this study can give in the field of physics? For example, are there possible tangible outputs that can be produced out of this, or any improvements in the scientific practices?
There certainly is. Now, one thing I didn't speak about was all the applications we currently have for thermophoresis. I was also working a little bit with an honours student who's looking at applying this effect to use it for desalination methods. So you can imagine if we actually get a concentration gradient in ionic solutions, this would be really useful for potentially using it for desalination. So understanding this effect well and how we can actually optimize this effect in particular, which is what, researching the theoretical basis of it does, means that we can better apply it to something like desalination. Another really interesting recent application was that thermophoresis is used in something called microscale thermophoresis, and this characterizes the sort of binding free energies of various biomolecules. And this was actually used to calculate the binding free energy of COVID spike proteins recently. So yeah, certainly very applicable, but it'd be good to know more about why it occurs.
Thank you so much.
Great. Do we have any questions from the audience? Please put it in the chat, or you can raise your hand, or from the other student presenters. So yeah, we have 2 questions from the audience. It sounds like sodium and chloride have their own preference and personality. Sodium and chloride bond together to form salt. Both prefer thermophobic. Is that why they bond together?
In this case, I don't think that is why they bond together. They bond together due to a charge difference in the ions. But in this case, we're not really looking at ionic bonding isn't a relevant effect in thermophoresis. So no, I don't think the fact that thermophobic is why they bond together.
Great. We have another 2 questions. So what amount of energy is contained in a thermoferrotic process? For example, could thermophoresis oppose an electrochemical gradient in ion channels, or is it too weak?
This is a really good question. It's actually a very weak process. So electric fields are much, much stronger. And no, it wouldn't be able to oppose an electrochemical gradient in ion channels. In terms of desalination, for instance, it's one method that does work. It's a stronger effect if you have a stronger temperature gradient. But you're right, it's still very weak on the grand scale of temperature scales. And to get any ion movement, you need quite significant temperature gradients, as you would have seen in some of the data I showed. So like if you're looking here, we see we need sort of temperature differences of at one stage, I think I was doing something like 100 Kelvin. So yeah, over a very short range.
Also, do you have any hypothesis about why there's an inversion point in sodium? Or could it be the atomic properties of Na versus chloride? For example, could it be due to the effect of the nuclear charge or solvation?
I suspect that in this case, the solvation shells show is the predominant effect. So I did actually look at this, and I didn't speak about this particular aspect of research here. But we also have to bear in mind that this is a really weak effect for single ions. So I wouldn't quite call this a conclusive inversion. I actually think the best way to probe this would be to look at other ions and look at whether it's a case of, is it a positive charge thing? Is it, the size of the ions? But the problem is to run these simulations, I was running them on a supercomputer, so for a very, very long time. So ideally, I would have liked to show comparisons there to be able to better explain any differences in inversion. So hopefully that answers a little bit better, but like most questions in this field, the answers are a bit murky.
Great. We take the last question from Martha.
Yeah, this hopefully is a quick one. Just on that slide where you had the results that you said hadn't come to equilibrium. Yeah. What makes you think it hasn't come into equilibrium there, as opposed to this being some real result that is just not what you expected?
Okay, this is a really good question. The reason why is because solvation entropy, it's hypothesized that it really should change with temperature. It's been shown that previously it should depend linearly on temperature from what I've read. But also this is sort of a well-known result in that the way we actually calculate solvation entropy is it uses two parameters. It uses the average internal energy of our molecular dynamic systems and the free energy. So it's got inherently more error than the free energy data. So that's why it generally takes it longer to converge, and why I do suspect it is a convergence issue.
Great. Thanks, Rosemary, for that great presentation. So this brings us to the end of our today's session. I'd like to thank our judges, Dr. Maria and Marina, for being here, and congratulate our student presenters for the great presentations they gave today. The recording for the session will be available online after the conference, and we hope to see you in other conference events this week. See you guys. Thank you.
Thanks, everyone.
Thank you. Well done.